Have you ever wondered why incredibly smart language models suddenly just get stuck when you ask them to do actual, real-world work? Welcome to Day 4 of our series. Today, we're unpacking the core architecture that actually fixes this problem. We're talking about the agent loop.
You've likely built or interacted with a standard chatbot, right? And, it works brilliantly for answering a one-off question about Python syntax. But ask it to do a multi-step job, like finding the 3 cheapest flights to Tokyo, cross-referencing your loyalty points, and then booking the best option, and it just hits a brick wall. It either hallucinates or it simply gives up.
Now, the reason for this isn't a lack of intelligence, it's actually an architectural limitation. You see, a standard chatbot is what we call a single-pass system. It takes one prompt, generates one string of text, and then completely stops. It has absolutely zero built-in mechanism to evaluate what it just did, adapt to a new piece of information, and keep going. By the end of this explainer, you're going to understand the exact mechanism that fixes this limitation.
To build our core intuition here, I want you to think about a junior engineer's first day on the job. If you hand them a complex debugging task, they don't just stare at the screen, hold their breath, and instantly type out the final fix in one continuous motion. That's not how it works. They work in a loop. They read the error log, they take a first step, maybe querying a database. They look at the result of that query, and based on what they see, they decide their next move. The agent loop is literally just this exact human workday, translated into software.
In AI engineering, we formally call this the react cycle, which is short for reason and act. It maps directly to our junior engineer's workflow through 3 distinct beats. First, think. The model analyzes the goal and decides its next move. Second, act. The system actually executes a tool, like pinging a web search API or a database. And third, observe. The system takes the raw result from that API and feeds it right back to the model. Think, act, observe. This heartbeat just continues until the job is done.
Now, you might be asking yourself, as a developer, why do we need this loop at all? Why can't the model just execute everything natively? Well, it's because large language models are fundamentally stateless functions. They have zero memory between API calls. Without the loop, the model forgets your entire existence the millisecond it generates a response. So the loop acts as the agent's short-term memory. It appends every action and observation into a growing context window, and then resubmits that entire history on every single turn.
Let's ground this technically. When you strip away all the industry hype, the agent loop really isn't magic. It is simply the runtime environment. It's the outer orchestration shell that manages state and executes tools. The LLM itself does not make an API call to a weather service or a server. The loop makes that call. The model is just the brain deciding which tool to use. The loop is the hands that turn that decision into real-world state changes.
At its core, an agent loop is fundamentally just a 20-line while loop in Python or TypeScript. It looks roughly like this. While the task is not marked complete, you call the LLM. If the model asks to use a tool, your code executes that tool. You append the result to your messages array, and you just loop back around. That's the big secret. It's literally just a while loop wrapping an inference call.
But as any software engineer knows, writing a while true loop is the easy part. Making sure it actually stops is where you earn your paycheck. A production-grade agent loop absolutely must have 2 stopping conditions. The first is a natural stop, where the model outputs a task complete flag. The second is a safety stop, basically a hard iteration limit. Because trusting an LLM to voluntarily stop on its own, yeah, that's a fantastic way to rack up a massive API bill by Monday morning.
Handling these edge cases is the real work of production AI. Without those safety stops, you get infinite loops. And as your loop runs, you constantly risk context overflow, which is where the growing history of tool outputs exceeds the model's token limit, causing the whole thing to crash. You also have to write programmatic interventions to detect if the model gets stuck in a hallucination loop, blindly repeating the exact same failed database query over and over again. So where does this architecture actually run out in the wild? Honestly, everywhere that requires autonomous, real-time adaptation. Take DeepMind's optimization of data center cooling, for example. They don't just ask an LLM how they should cool a room. No, they implemented agent loops that continuously monitor live sensor telemetry. The loop reads the temperature, thinks about the optimal setting, actuates a change in the cooling system, and then observes the new temperature. It's the react cycle applied directly to physical infrastructure. We see this exact same pattern in logistics networks, rerouting trucks, and algorithmic trading agents navigating highly volatile markets.
However, practitioners do have to factor in the architectural tax. Iteration is not free. Internal telemetry shows that a single agent loop task consumes roughly 4 times more tokens than a standard user chat interaction. If you build a multi-agent system, that can easily jump to a 15 times cost multiplier. As a developer, you are deliberately trading a higher compute budget for autonomous execution. It's a trade-off.
To summarize today's explainer, the LLM is just the brain. The agent loop is the runtime that gives it memory, executes its tools, and turns its thoughts into actions. The difference between a fragile chatbot and an autonomous agent isn't a smarter model, it's the loop. But this leaves us with a critical question to chew on. As these loops get faster and are given access to more powerful tools, how much autonomy are we truly comfortable handing over to a piece of code that writes its own next steps?